to the launch with the end of this year. So in December, we're sending another 4 satellites. Next year, 2021, we want to send another satellite with the optical payload, which is Stork and Sova. And our main goal is, of course, to establish it Earth observation constellation. And the first phase of it is to send 8 satellites in 2023. So that's what SatRevolutions do. And right now, I think I pass the voice to my friend from AuroraSat. If you are ready, the view is yours.
Yeah, hello everyone. So I'm Perttu Riepas, the CTO of Aurora Propulsion Technologies. Many of you might have heard about Aurora, but I'll just tell briefly about what we do at Aurora. So we are doing propulsion systems, mainly for CubeSats as well as small sats. Right now, our two products, what we are launching at the moment is a Resistor Jet propulsion system. So we have both a single thruster variant, which is the world's smallest integrated propulsion system at about 30 grams of full system mass, including propellant tanks and control electronics, as well as the attitude control module, which is a 6 thruster integrated attitude control system with only propulsive attitude control. Then the second product is the plasma brake, which is a deorbiting system. So basically a propellantless electrostatic tether system for deorbiting both CubeSats and bigger satellites. Basically, the bigger variant works for up to 1,000 kilogram satellites for about up to 1,000 kilometer orbits. So what I'm talking about today is specifically the AuroraSat 1. So that is the mission, of course, that we are flying with SatRevolution on the December launch. So yeah, let's go to the next slide. Thank you. So the first payload there. So the AuroraSat 1 is our own in-orbit demonstration mission with 2 payloads. The first payload there is the Resistor Jet Attitude Control Module, the product naming being the ARM-A, Aurora Resistor Jet Module Attitude. So we have 6 thrusters, as you can see in the image. That's the actual flight model image being taken last week, actually, so very recent imagery. So we can provide a full 3-axis control at about 0.35 unit volume and only 180 grams dry mass. So really the system is quite light. The single thruster performance is about 1 millinewton of thrust at about 100 seconds ISP. However, the ISP is something that we are intended to actually measure from the actual AuroraSat 1 mission, because estimating these kind of numbers in vacuum chambers is often difficult. And also the other thing that we want to measure on the mission is the minimum impulse speed. We are hoping to achieve what we've estimated, which is less than 10 micronewton seconds, because in that case we can actually support even a 3-year CubeSat mission of a 3U CubeSat with very high precision attitude control with no reaction wheels required for the system. So basically, instead of having a system with magnet rotors and reaction wheels, you can just have our propulsion system that will be able to provide the attitude control at the same accuracies, or of course, depending on the mission, but where you can actually run the mission to anywhere. So for example, there's quite a few GTO or other higher orbit missions for CubeSats coming up. And for that kind of missions, of course, magnet rotors are not enough. So we can provide the attitude control for that. Our power levels are something like 3 to 4 watts per millinewton, depending a little bit on the variant. So yeah, that's what we are now flying and showing that it actually does work in a real world scenario, and showing and also experimenting with the angular accuracy that we can achieve for such a system. Of course, the AuroraSat-1 is only a 1.5 unit CubeSat, so it's a very small system. Simply because we just don't need anything more for our systems, but that's going to be a very good demonstration for this product. Let's go to the next slide, please.
I just want to add that if you want to ask the question, you can do it on chat, or there will be time after the presentation.
Yes. Yeah, I have the chat open here as well, so I can answer any questions as soon as they come up. On the plasma brake, that is our second payload and in orbit demonstration mission on this satellite. So this is the plasma brake variant of the the CubeSat variant of the plasma brake. Sorry. So it is intended for satellites up to maybe 20 or 30 kilograms. On the AuroraSat-1, we actually have a dual redundant design. So we have two plasma brakes just because we basically had the space and mass budget, and we want to get to prove not only one deployment but two deployments of the micro tether. So the plasma brake is a system that uses a micro tether, which is basically a very light tether. The benefit there being the safety, the inherent safety of the tether, because the aluminum wires that the tether consists of only they are 50 micrometers in diameter. That's about half of a human hair, which means that even if there was a situation where the tether would hit another satellite, the damage caused to the other satellite is less than the daily bombardment of micrometeorites. Basically, even if it hits a solar panel directly, there will be no damage to the system. So it's absolutely safe for deorbiting. This is very much our target, to have a system that is actually scalable for up to thousands or tens of thousands of satellites in orbit, when we are actually now scaling up the numbers of satellites very far. The device itself it can be used in the bigger configuration up to about 1,000 kilogram satellites, up to about 1,000 kilometer orbits. So it's very versatile for different satellites and orbits. This has been basically researched in the Finnish academia. The Finnish Meteorological Institute has done a lot of research on the theoretical side, as well as a couple demonstrators. They've had some problems with the deployment, and they are actually about to launch another demonstration on their part. But we've done it especially for a CubeSat use case, and we are also providing that commercially, unlike the academia here, who are mostly doing that for research purposes. So our aim here is that basically after we have done the reaction control system testing on the AuroraSat-1 mission, we will move on to the plasma brake mission, and we will first deploy one of the tethers, see that the deployment was successful, and start the deorbiting procedure. We actually have a slightly shorter tether on this mission, so that we can actually gather data for a longer time. So we are expecting the deorbit time to be something like 1 year. On the 550 kilometer orbit that we are going on to, the drag is something like 10 times more than the air drag post onto the satellite on the same orbit. So it is quite a bit faster than without any systems, but it will still take a decently long time. That of course depending on things such as solar cycles and so on. And once we've done most of the deorbiting with one of the tethers, we will then deploy the second tether to verify that is functional as well. Yeah, let's go to the next slide. So the second part of this talk is basically our story about this mission. So let's say that our timeline for this mission was a quite quick one. So we actually came up with the idea of making our own satellite for an inner orbit demonstration in February in the SmallSat symposium in San Francisco. And basically we met with Momentus there, and they told us that they have a launch coming up in December. And that sounded very, very good for us. So 48 hours later, we had a signed contract. But on our side, what probably even Momentus didn't quite know at the time, but we had preliminary designs for a little bit different use cases. So basically, both of these products had to be designed from scratch. The thrusters themselves, of course, were a tested design at that point already, but the whole tank design, as well as most of the electronics and the whole mechanical subsystem, were basically designed from scratch. And also for the plasma brake, we only really had the tether manufacturing, as well as some very, very initial models for the basic real structure for the tether deployment. So yes, that was going to be a very tight timeline, because we had to have the flight model testing done by end of July. And that means that in 6 months, we had to do a complete design as well as manufacturing of the systems. And then Corona hit. So you can imagine that after having a very tight timeline for a satellite project, having Corona did not help things. Let's go to the next slide, please. So what really happened with Corona on our part? The first thing was that we lost the access to our workshops. So the workshops that we are doing all machining in-house. We don't subcontract any of the mechanical parts, but we actually machine everything ourselves. That is one of the reasons why we knew that we can actually make things in this timeline, because of course subcontracting of mechanical parts always takes more time and brings more complexity. However, because of Corona, our machine shops that we are using, which are on the university premises here in Finland, were closed down. And this meant that for more than 2.5 months, we were actually not able to do any machining. This was basically the time when we were supposed to build the engineering model for the system. So this means that we really we weren't able to do any testing or prototyping for the mechanical design. We only then later on got to make the environmental test engineering model, which was kind of the only prototype we had time to do, and then directly go into manufacturing the flight model. On other things, subcontracting, well, we ended up doing some mechanical parts subcontracted because of the situation with the machine shops. That was not a good thing. There's always some problems, and that took a lot more time. So definitely there's always some problems with that, and of course it's a balance on what you need to invest in on yourself and what you can subcontract. But we are very happy that now we have a good workshop that we can work at, and that we are able to do all of that work ourselves now. Then a very interesting story is the rusting aluminum. So we are using 7075 aluminum for our tank design, and it turns out it doesn't like a certain cleaning agents. So basically, after making the 2 candidate flight models, we had first machined one of them, and then machined the second one, and then cleaned both. And the one that had been basically dirty for a little time had started some chemical process with the aluminum and with, I think, maybe the cutting fluids or something. And even after cleaning, everything looked just fine. and we cleaned it, we did inspections, and it was just fine. We packed it up for integration in about 2 weeks later. And 2 weeks later, it comes out of the box and it's rusty. I mean, that's the only way that I can describe it. It looks like it has rusted in the on the surface. It's aluminum, so it's obviously not rust, but some other chemical reaction. But that was definitely a surprise to see that. So we had to fall back to our other tank frame, which was luckily good enough. Then other minor stories from the Corona times. We had a load driver that we are using for the solenoid valves that we have on the system. And turns out you cannot trust a load driver to actually insulate the driving current from the logic current. So we actually burned a couple microcontrollers because of the load driver basically generating about 1 volt spikes to the logic driving pin, even though that's supposed to be an input for the driver. So that kind of things as well. It's completely used within spec, exactly what it's designed for, but it just doesn't work for that. Very, very interesting surprises in the middle of all of this, as well as some of the failed welds. So yeah, 7075, again, we had welded it, we had inspected it, everything was working perfectly, the welds were strong, they were visually looking very, very good when inspected with a microscope, and about a week later, they were cracked. They had just developed a crack throughout the weld, and they were basically not even attached. So yeah, do not weld 7075. And these kind of stories, like I have hundreds of these stories from the last half year, and how we had to fight through all of these small troubles. Of course, there's always these kind of troubles in space technology projects, but combined with Corona and other things, it was a lot of not so many not so nice surprises along the way. But let's go to the next slide, and I can tell a little bit about what actually went right and why were we actually able to pull through. So the saving graces. So we did get back to the machines up by before end of May, basically. That's thanks to Auto Design Factory. We were the first external party that they opened for. So as soon as it was legal for them to open their doors for anyone, they opened them for us, and we were actually able to then machine these parts. Then another very interesting thing what we did is an over-the-air update capability for the microprocessor on board. We're using an MSP430 FR family microprocessor, and basically in the beginning of the project already, we decided that, hey, the attitude control system will require complex algorithms to be developed that we want to test. And that development is something that we would really like to do also after we've gotten some feedback from the in-space testing. When we've tried a PID controller for detumbling, we understand the problem so much more than we want to develop the control algorithms only then. And in general, just for saving time in this type of very tight timeline project, we wanted to have the opportunity to fix any software issues as well as make new software. So we are using the same processor on both of the products, and we have the same capability for over-the-air updates. So we really didn't do much other than the over-the-air update and very basic functionality. We are actually able to do something like, well, more than half of all of the experimentation with the software that we ended up programming. It was a bit more than we were expecting, but still the over-the-air update really gave us it freed us from the stress of needing to complete the software in time, and we were able to concentrate on making the software that we have done work doing the test for that, making sure that that is correct instead of trying to cram as many implemented functions into there as possible. For manufacturing, definitely a very important thing for us was that we did some extra models. We didn't just do a single part for the flight model, but we actually did 2 or 3 copies of every part, which meant that when we had some problems with certain components, we were just able to swap them for other ones. One very, let's say, positive experience on subcontracting was that we subcontracted the PCB assembly. We subcontracted it to RUAG Space Finland, which of course RUAG has very long experience with space electronics. So it was a very easy case for them, and they knew exactly what they are doing, which saved a lot of trouble from us, because during the project, working with some of the prototype PCBs of these final ones, we had quite a few times some cold wells and so on, because again, we were not actually working from the actual workshops that we usually work from, but from home. Most of us were just working from home. We had an oscilloscope and one power supply that we were taking from one electrical engineer's home to a software engineer's home, and so on. So in those situations, we wouldn't have been able to really do the PCB assembly on a level that we would have been confident with for an actual flight model. So we are very happy that we did that, but definitely when subcontracting, if there's no extra time or extra budget, it makes sense to do it with a company that is actually doing space technology, if just possible. And also the few tests that we did have time for, basically our time reserved for testing of the systems was just used for manufacturing because of the timeline shifts. But the few tests that we had time for were very, very important. So I really cannot stress that enough. Testing is always important. And yeah, but by far the largest factor for sure was the incredible dedication of the team. There was the last week, let's say, of integrating the systems and doing the last fixes on both mechanical and electronic subsystems. That was a long week, but in the end we pulled through, and now basically everything is ready. We are just waiting for a last delivery on a subcomponent for the platform, and we will be doing basically the full satellite has been assembled, and we know that everything is ready for final assembly, which will happen in a few weeks. Yeah, there is at least one question. So in retrospect, what kinds of information would have helped you do better with selecting subcontractors? Did you go with companies that generally perform space-rated work? So yeah, on the PCB side, of course, we did go with a company that does space-rated work, and that was a good idea. But on the mechanical side, I don't think I could really even much help my past self with that, because there isn't much companies that would be doing space-rated work. At least in Finland, there are basically none. Within Europe, there will be a few, but the mechanical side is something that is because we are not only making a typical like satellite frame which has tolerances of like 0.1 millimeters. We have tolerances of maybe 5 micrometers, even a couple micrometers in our most delicate parts because of our thruster scale. So really we were able to find the few people that are able to do that scale of work, and those are the clockwork mechanics. So actually the school of clockwork mechanics is where, okay, technically they are called nowadays micromechanics. We have a couple of those that we hired, and they know the others that have been studying in the same school and have some companies, and those people were the most important for us because they can actually do work on the small scale and exact tolerance that we need. But I'm still not aware of any companies that are doing space-rated work on such small parts. Our, for example, our thruster piping system is based on a 1.6 millimeter or 1/16 of an inch piping system, and we do all pipe attachments as well as welds of the thruster tips around that size. And you can imagine that when the part size is that, the tolerances are very, very small. So yeah, still not quite aware of what could even be subcontracted, let's say, easier from other players. Yeah, any other questions?
Yeah, I don't see any more questions. I think we can forward.
Yeah, well, let's go forward. Thank you, Gregor, for the opportunity. And yeah, you can always be in contact with me if there are any questions or if you want to buy our products.
Yes, of course, Justin, if you want, you can go to our website on SatRevolution and find the information on our mission section where the Aurora is, and then you probably find a contact. If you cannot find, you can always contact with us, and we give you the contact to the Petru. That's no problem. So let's move forward. If that's all from your side, Petru, and we have no other question, I think we will wait like a few seconds. There is no more question. Okay, for the rest of you who are following our big prize, the clue for a prize today is 2016, so 2016. If you don't know about what is going on, please visit our small sat schedule site on the SatRevolution.com. Thank you, Petru, for joining today and for all information. Thank you all of you for participating, and have a nice evening or nice day, whatever of the time zone you are. Thank you, and see you tomorrow on the next webinars. Have a nice day or evening.
Thank you, everyone.